Hello everyone, so welcome to this webinar, wherever you are. This session is going to be about dependency management with Gradle, fundamentals, so it's at least a two-part session. We're going to talk about the second part in the end of this webinar. So first, going to introduce ourselves. Let's see, so I'm Cédric and I'm today with Louis, from the dependency management team. So we've been working together on dependency management for about a year, but before that I actually joined Gradle before and worked on different topics, performance, software model, different things. And today this session is really about dependency management, so you will have the voice of the people actually working on this topic today. Louis, if you want to say a few words about yourself.
Yep, so welcome everyone. Louis here. So indeed, like Cedric, working on dependency management since I joined Gradle a year ago. And before that, being a Gradle user somewhat and having some kind of interest, all kinds of interesting fun in programming. Let's go.
So first, just a small introduction about Gradle itself. I don't know if everybody here is actually using Gradle today, so probably some reminder about Gradle's purpose is interesting. So first of all, Gradle for us is a build tool and automation tool, which is based on the JVM, so working on the JVM, implemented in Java, open source. And this is a tool which is actually not specific to the Java ecosystem, so it's not because it works on the JVM that you cannot build different types of projects. So in particular, what we want to say, and this is interesting, especially in the area of dependency management, is that Gradle is a system which is agnostic. So you can build Java applications or the Java ecosystem applications, so Java, Groovy, Kotlin, Scala, whatever. But it also works for the native ecosystem, so C, C++. Probably lots of you today are actually going from the Android ecosystem and reaching Gradle through the Android ecosystem. And what we have also from different people in the community is actually plugins that work for Python, Go, and what I like to mention often is that this presentation is using ASCII Doctor, and it is built using Gradle and using some dependency management features of Gradle. So what I would like to mention in particular is that Gradle is agnostic. Gradle lets you build different systems, and when we talk about the Python in particular system, some people actually wrote some plugins that leverage the dependency management features of Gradle to implement dependency management for Python. Also, we can mention the JavaScript ecosystem where there are some plugins existing too. So really a rich ecosystem around dependency management. Next, just we need to say a few words about Gradle Enterprise, which is not this time the open source project, but something that Gradle provides commercially. And this is basically about getting insights about your builds. And I'm going to show some demonstration later about something called build scans. This is actually part of Gradle Enterprise, and we would be happy to answer questions about this. But this is really not the topic today. Today we're going to talk about the dependency management features, but you're going to see some build scans. Louis, can you tell us a bit more about this topic of today?
Let's try to introduce why do we nowadays talk about dependency management and where does that come from? Well, a long time ago, if you were a Java developer in the early days, what you had to do was create your Java source file, go into that folder where they lived, compile them, then go to that output location you've specified, finally create the jar, which is the binary archive that represents your Java library or application. And if that was a library, you may have another project that, in order to be compiled, needed to reference that first project you just built. And you did that again with even more parameters to the Java compiler. Let's say that works when you're trying things initially, but it doesn't last long. And so what happened is that tools appeared. And the first generation of tools, and to name it, as an example, was really to help you build and package your Java library or applications. These tools did not take care of dependencies. What they took care of was really building all the parameters that these different command line tools required and abstract the definition of those. And so usually what you had to do in order to use dependencies was go to some project website, SourceForge anyone, or even Freshmeat for the older folks around there, download the jars from the project website, put them all in a lib directory or something equivalent, depending on your project setup. And usually, in order to have reproducible outputs, you would save them in the source control as files, which is not always ideal because most of these tools were really good at handling text, but not so much binaries.
So something to mention is that actually we do have some customers that still work in that era, and Gradle still offers you a way to do this, if you really want to do this.
Yeah. So when you do that, the first question you're asking yourself is, should I use the source or the published component? And of course, when you look at the source, well, they give you some kind of confidence because it's text, you can read it, and so you can verify that it's not been tampered with. However, you've got to rebuild, which is slow, but also the versioning problem comes up. Like, should you use the source control management systems version? Should you provide something else? I mean, it all becomes like really difficult to decide. On the other hand, if you were to consume binaries, yes, they're stable. Like if you download the same binary multiple times and you verify its signature and you know it's the same, you're pretty sure it does the exact same stuff. It's faster. You don't have to rebuild all your dependencies. However, it requires the source who built that binary to be trusted, and the metadata wasn't there. Like depending on the level or the quality of the documentation of a library, you were not always really, it was not always really clear which were its dependencies. So all of that happened over a couple of years, and what also happened is that the Java ecosystem really took off and grew a whole lot, with a lot of people putting libraries out there to be reused. Java was already providing quite an extensive standard library, but still people had other needs, extra needs. And the world around was evolving, so the needs were evolving, and hop, there you go, a whole lot of libraries being produced. And so that means that the next step, which happened quite naturally in a way, was to start with dependency management. And you had two tools like Ivy and Maven. They would do that for you. They would take care of your dependencies. They would suddenly decide that libraries have known coordinates. And in order to publish an Ivy or a Maven library, you had to buy into that representation of your dependency. You were publishing those to repositories. Whether they were public or private doesn't matter. You were publishing these dependencies with metadata in addition of the binary. And what these tools provided was really that automation around the transitive aspect. And that really was a game changer, because suddenly the only thing you say is, oh, I need Hibernate. And the fact that Hibernate requires code generation libraries or other kind of things is no longer your problem. At least that's what we thought. We'll talk about that later. So one item that's important to understand, because we get that as a question quite often, it's the metadata aspect. Maven is not equal to Maven Central. Maven is a lot of things. It's a build tool, and in that, Gradle is a direct competitor. But the Maven POM is a metadata format. And in that, Gradle is a user. Gradle can consume Maven metadata. And Maven metadata and the relevant artifacts are published to Maven repositories, where you can find them with the metadata, and Gradle can consume them. And you've got other tools out there that probably can consume Maven metadata. So with that said, well, Gradle joined the party. However, a decision was made within Gradle to say, you know what? None of these options are invalid by themselves. So we should probably offer them, because for different reasons, you may require a different system. And so Gradle will work with a lib folder or a custom repository that just has artifact by names. Of course, that means you give up on the transitive dependency management. If you want the transitive dependency management and the libraries you're consuming are either coming from Ivy or Maven, good news, Gradle can consume them. Beyond the fundamentals, so beyond this webinar, we will also see why Gradle deemed necessary to have its own metadata format. And that metadata format has been announced stable with release 5.3 of Gradle that was a couple of weeks ago, or a week ago.
A week ago, yeah.
With 5.3.1 being released earlier today. And we'll even see that Gradle added even more options for handling dependencies. So with all of that, we thought it would be interesting to start with a small project that has a number of the dependency management concepts applied, and based on these examples, then go on with defining all of that. So, Cedric?
Okay, awesome. So this is really, as we explained, a very simple project. So first I'm just going to show you what it does and then explain how it is structured. And this is just something that we implemented for this webinar, and we all love Git, and sometimes Git can be frustrating, and actually we have tools to deal with this, and this one is just a tool to extract the number of committers that we have on a Git repository, so something super exciting. So it is composed in two parts. So one is the CLI, and I, as a user, want to interact with the command line and give the options and tools. And then a second module is just going to be the actual thing that is going to communicate with Git. So for those of you who are not familiar with Gradle today, this is just a project that has two submodules which are declared in the settings.gradle file. So nothing really fancy. And if I go to the command line and try to build this with Gradle, it's just going to be super easy. I'm just going to do Gradle W and then build, which is going to build my project. Here we go. And now if I want to try this out, I'm just going to go to the CLI command line subdirectory. Sorry, I'm not in the right one. Should be this one. Because as I mentioned, actually, the presentation is built with Gradle. And we get an error. What is this guy doing? Oh, I'm not using the right version. That is not expected. Okay, this is the JVM version, you know. So, because to tell you, I'm not using Gradle with Mac today. Well, I'm using Gradle with a Mac today, but I'm used to Linux. Anyway, so I'm not going to show you the command line. It's not really interesting there. But the idea is that if I run a command line, it's going to tell me for this repository what committers we have, and I can show you how it works. It's just a simple code saying, yeah, please, git utils, give me the number of committers. So just find all the committers and compute the size. So not really something really fancy, but we already see that we have two different things there. We have an external dependency on something which is not a library I wrote, and then a dependency on my library. So how does it work? So with the Gradle build files, if I go to the CLI build file, what I have is something which is not really super complicated, actually. I'm just saying I have a Java application, so I apply two plugins, and then I define some really simple things like when I implement this project, I need a dependency on my git utils submodule. And then I also have a dependency on this Pico CLI project. Okay, so already, just looking at this thing, we already see that we have two different kinds of dependencies. I'm talking about implementation. Everything like that has a meaning, and we're going to explain what is this meaning and what you can do with that. So something important to mention is that if I want to know what the dependencies of this CLI is, I have some tools to do that with Gradle. So first, I'm going to show you the second project, which is my Git utils module. And this one is just what we call a Java library. So it doesn't have an interface with a command line, so it's not an application, it's really a Java library. So something that is consumed by my main CLI module. And this one also applies a plugin, also defines some repositories, and also has some dependencies. And as I'm using some logging, I'm using the SLF4J API logging framework, and I'm using this JGit library that, again, we didn't write, which is the Eclipse one. Of course, with the good engineering practices, we're also using some tests. So I'm using JUnit 5, and because for logging, just the API is not enough, you know that I have to add some binding for the logger to be able to log something when I run the tests. So again, we have something there that allows me to do that. Okay, so what does it mean when I want to know what the actual dependencies of this guy are? So I can go to the command line again and go to the project, which is the Git utils one. And if I just look at this build file, I'm just going to check, this is exactly this one. So in Gradle, what you do is just Gradle W dependencies. And I want to work actually on the Git utils project, so Git utils dependencies. And I'm going to add a parameter there, which is the configuration I want to resolve. So I'm already starting to use some names. Configuration is an important name, and I'm going to use the compile class path. All right, so what it shows there is that when I need to compile this guy, I need all those dependencies. So there's nothing really interesting in the dependencies I bring there, but if I go to the test compile class path, I'm going to see that actually I need more because I need to add the JUnit dependencies to this mix so that I can compile the tests. So the compiling the application and compiling the test of the application require two different sets of dependencies. And that's exactly what we are mentioning here by separating the implementation and the test implementation. Okay, so now if I do the same, but for the CLI project, and I go, Gradle, please tell me, what do I need to compile this CLI? So dependencies for CLI and the compile class path. And what we see is actually something really nice, which is that I need this Git utils project and I need this CLI library, but I don't need SLF4J. I don't need Git to compile this project. This is something that is really only needed for the Git utils subproject, but not for me. However, if I need to run this application, so run the CLI, so I'm going to check the runtime class path. This time, I need all the dependencies. So this is an important aspect of Gradle, which is to understand what the different kind of dependencies we have. And this is also something important for the optimization of the whole building aspect. Because when we build a project, we know that we need less dependencies basically than when we run something, or when we run the test, or the test fixtures, or the functional test, or whatever. So you have different sets of dependencies, and they don't belong to the same different things. Okay. So this is just for the list of dependencies, and now we're going just to play around with those different build files. So for those of you who are familiar with Gradle already, you may notice that actually I use this implementation there. And usually what you find on Stack Overflow, whatever is not implementation, you find this, compile. So this works. I just need to mention that this works, but you shouldn't do that. This is deprecated, so this is something that we call soft deprecated. So this is really something that has been there in Gradle for years, but you should avoid doing that because it doesn't give enough information for Gradle to resolve properly, and actually it leaks dependencies. So don't do this, and instead really say, no, implementation. So implementation, the meaning of implementation is to build this specific project. The implementation of this project requires this. And I could say something like compile only, again with some coordinates, conf bar. So this is the version. So when I do this, actually, I'm saying, yeah, to compile this project, you will need this library, but actually to run it, it's not going to be necessary. So you have different aspects.
Yeah, one of the clear aspects for that, for example, is annotation processing or annotations themselves that are needed at compilation time, but effectively no one needs them after that.
Yeah, or sometimes you can have a project like you're going to deploy on Tomcat, and some libraries are already bundled, so you know that you don't need to add them. Okay, so now I'm just going to play a bit with this notation. So implementation is something that is just telling me use this dependency as an implementation, but I can actually tell a bit more. Something which is really, really nice, I guess, is this because method. So this one is just saying, actually, this is the library we use to pass the command line arguments. So this is not a comment. This is actually something which is declared on the library and declared on the dependency. And one of the interests of doing that is that, again, if I go on the command line, I have a nice command here, which is called the dependency insight report. So before we saw the dependencies task, now it's called dependency insight. And this one is a bit special. It needs the configuration you want to tell something about. So tell me about the compile class path, but I'm going to focus on a specific dependency, and I'm going to focus on this Pico CLI dependency. So when I do that, Gradle is going to tell me, actually, you need this library because the library we use is to pass the command line arguments. So in this very special case, this is not super interesting because it's obvious it's in the build file. So why would that query for something which is written? But actually, this is something which is transitively available. So if you have a dependency which comes from whatever, you just have to request Gradle, please tell me something about this, and it's going to tell you where it comes from. And if you took the time to mention why use this, this would be available to people. So a colleague of yours could just ask, yeah, why do we need this library? And actually it's written, so much nicer. A bit later, we're going to see something which is called a version block, which is something interesting. And this is also where you would get some special parameters like false, or well, it's is false on Kotlin, not the Kotlin DSL. And changing, which is also something that we can discuss. So you have a lot of different things there. The nice aspect of using the Kotlin DSL is actually when I wrote this, it's actually red. It tells me this is not the thing. But if I do is and then press command space, whoops, it's actually telling me this is a flag that you can use. So you have completion available, which is pretty nice. All right, so this is the default changing module. Okay, so now what I want to mention is a bit about these repositories that we see here. So repositories are, as you explained a bit before, this is the location where we fetch external dependencies. So here we have two different dependencies. One is the project dependency, and the other one is the implementation dependency on something which is not local this is published on an external repository. So I'm just telling Gradle, if you need to find this, please look at Maven Central. So when Louis was explaining that Maven is not Maven Central, this is exactly that. If you want to consume dependencies from Maven Central, you have to declare this repository. So if you come from the Maven background, this is a bit weird because it would use this Maven Central by default. But actually, with Gradle, you don't have to use Maven Central. If you want to use something else, you can. And actually, you have different repositories there. So Maven Central, I can also use JCenter. For people using Google Android, you have the Google repository. And if none of those guys is actually the one that contains the dependency that you're using, because you have, say, an Artifactory repository, you can actually declare something there, like I'm going to declare a Maven repository, and this is going to be the URL for this repository. So, blah, 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 this is my company internal repository. So this is actually declaring a list of repositories. All right. So something interesting to mention is if I do this, this is going to resolve the dependencies. So I'm going to, again, Gradle CLI Dependencies and configuration compile class path. So if I do this, this is, what did I write? Dependencies, sorry. If I write this, what we see is that this has been resolved. If I remove Maven Central there and comment that out and resolve again, this shows me that actually we couldn't find this Pico CLI dependency. And often people tell us, this is weird, because now if I comment this guy and actually use, well, just leave the configuration of that, but use the runtime class path, I don't find SLF4J, I don't find JGit, I don't find Pico CLI, and this is a bit strange because in the project Git utils, actually the repositories are defined. There is something that tells me, hey, you should fetch that from Maven Central, so why doesn't it work? And one of the reasons it doesn't work is that we have to make sure that everything comes from the right repository, from the consumer point of view, and that dependencies have not been tampered with. So the repositories are declared on the consumer and reproducible on the consumer side. And the producer can use whatever repository they want. It's always the consumer that decides where you need to find the dependencies. So you have to duplicate this information. Last, before I hand over, well, actually I have something else to show, but I can't. So here you have a list of repositories. So if I do JCenter and Maven Central, what does it mean? It means that I define two sources where I can find those dependencies, external dependencies. But they are searched in order. And again, this is for a reason. This is to make sure that we can reproduce the builds. So imagine that this dependency is not available in Maven Central. We would first try to find it from Maven Central and then from JCenter. Which means that if you do something like this, you're in a very bad situation. So whenever you see Maven Local in a build file, it is likely that you don't want that. And Maven Local is actually that directory that you have in your home directory, which is the .m2/repository directory. And this one is something that is a cache for Maven. And often people just want to get some dependencies from the cache. And so they add Maven Local, but they should not because Gradle has its own cache. And that's not just a reason not to use that. The main reason not to use that is that who knows where the dependencies come from in this Maven Local project repository. So if I have 10 projects and I work only on one project, actually all the dependencies for all the projects, so everything I've done on those 10 projects are going to contribute something in this Maven Local repository. And worse than that, it means that if I'm playing locally and tampering with a dependency or adding something in the Maven Local repository and then removing it, a build could pass on my laptop, but not on Louis' one. So this is not reproducible. So there is actually one use case for using this, which is you need to share some projects between Gradle and Maven. So you have a module built with Maven and the other one built with Gradle. And the only way to do that with Maven is actually to publish, so install the result into your local Maven repository, and then you consume that from Gradle. But a better way to do that would be to have actually a company Artifactory or Nexus or whatever repository just to publish something and have Gradle resolve everything from the local. Okay, so this is just about these the repositories, and now the last thing I want to show you is this implementation thing, why it is important, especially in the case of the Git utils one. So when I showed the dependency trees for the CLI, we can see that the runtime class path actually contains this SLA4j API. So if I want to use SLA4j in my CLI, say in this class here, the main one, and I want to add a logger, well, the IDE would not tell me anything about the SLA4j logger because it's not available. It doesn't see anything regarding SLA4j, and this is because the library is actually declaring that this is an implementation dependency. So implementation dependencies do not leak to the consumers. So this is not part of the contract, if you will. If you really want to make this library part of the contract, use the API keyword instead. And this would make this library available to the consumers because you're saying, actually SLA4j is part of my API. So I can refresh the project, import the changes. And now if I again try to show the logger, SLA4j is available. Just something to mention, in any case, this is a bad example. SLA4j is not leaking into the API there, so it shouldn't be an API dependency, it should be an implementation dependency, really. And this means, this means that you need to duplicate this again in the consumer. So as an implementation detail, the producer, the library, uses SLA4j, and as an implementation detail, my application is also doing that. So the two of them have to declare that. So it's always a design decision to say, is it an API dependency, an implementation dependency? And in general, the recommendation we give is just start with an implementation dependency so that you don't leak everything. So we just manipulated a lot of different concepts there, and now we're just going to explain all those concepts and how they match in the dependency world.
Cedric mentioned it a lot. We need to get these dependencies. And so the from a repository to your machine is important for Gradle. I'm not going to repeat much of what he said. So he talked about the order, but Gradle also has lots of smarts so that we don't download files all the time. So the ordering is important. Cedric said that, he explained it. With a recent Gradle version, we introduced the ability to filter what a repository serves. So that, for example, you could say, these Android artifacts, they can only come from the Google repository. It has been shown recently that some repositories that don't have the official version of a dependency would be hijacked by hackers that would deploy a bad version of the dependency that would then do bad things in your application. So this is starting to be really important, and the feature in Gradle will help you with that.
Just to add on this, so especially if you have multiple repositories, this becomes super important. Yeah. Because if you have, say, JCenter in the first dependency, the first repository, and Google as the second one, anybody could publish something on
JCenter, yeah, so to shadow what would be in the Google repo. But have a look at the documentation. Don't forget that if you whitelist something in a repository, it does not automatically blacklist from the other. So you have to be explicit about that as well. Maven Local, maybe one thing. Remember, Maven Local is not strictly a repository. It's rather a cache for Maven. And so one of the things that will trip Gradle is partial download of modules. So for example, if you've only touched the main artifact and you're looking for a classifier, Gradle will not find it, even though it will stop, because it will find the metadata and the main artifact in Maven Local. So there be dragons, beware, remember the valid use case though. And metadata and artifacts are downloaded concurrently. However, the way Gradle search for binaries is interesting, because so the order of the repository matters, but also Gradle attaches importance to the source of an artifact. And so when you're requesting that SLF4J dependency from Maven Central, what Gradle will do, if it doesn't have already the information, it will try to know about this artifact, getting the digest of its metadata, the digest of its jar, and if it gets that information without having to download the file and realizes the file is already available locally, we'll just use it. By the way, Gradle will leverage Maven Local for doing file copies over internet downloads. This is not the same as declaring Maven Local. This is something that happens transparently and is only done if the hash of the file match what's requested.
So it's just a performance optimization.
Exactly. And so as a consequence of that, if we were to take the project Cedric used and change Maven Central from JCenter, the first time we ran with that modification, Gradle would issue a series of head requests towards JCenter and probably download not a single metadata or jar file, because they've been downloaded from Maven Central, and we seriously hope they're the exact same. And that means we have the file locally. So with the head, we get the hashes, we know that we've got the files, job's done. That's pretty much everything we had to say around repositories. So if you do have questions on the topic of repositories, make sure to ask them, and we'll try to get them by the end of the webinar, or if not, as a follow-up via email. So let's go down to core concepts. So Cedric mentioned tons of information. So let's start again from the beginning there and try to build a really good understanding. That's why this part is called fundamentals, because all of that information is required in order to understand why Gradle offers higher level features. So first thing first, a module. Well, that's a piece of software that evolves over time. The module is the word you will see in Gradle documentation. Sometimes it's dependencies, sometimes it's artifacts, sometimes it's binary. And what happens is that a module has an identity. And nowadays, pretty much the Maven notation one, so it's a group name and a version. Even Ivy repository tend to abide by that setting, so that's pretty much a reference. And so here we see an example extracted from the code Cedric showed, which is the SLF4J API artifact, which has the org SLF4J group name. SLF4J API is the name of the module, and we're talking about version 172. In order to use these external artifacts in Gradle, you leverage configuration. And so in the context of dependency management, and for most users, a configuration is a named set of dependencies. Some more advanced usages require you to view the configuration as a way to get access to resolve modules and their artifacts. This is usually the things that a plugin has to do behind the scene, but it's also sometimes useful. For example, the classical question we get sometimes is, how do I copy all my dependencies to a given folder? Like if I want to build my application zip archive. And so an example that Cedric mentioned a couple times is implementation. So with that information, it's important to understand that these configuration map to concepts and represent something real that Gradle manipulates. So Cedric used mostly implementation and talked a little bit about the API configuration as well. Maybe one slight side note. We're focusing on Java in order to give you all the examples and the explanations, but these concepts are exactly the same that are used in the native landscape. It's just that the details change, but the concepts remain the same. Yep. So I've got my API, I've got my implementation, but actually we've talked about it slightly. There are more than that. There is also compile only for these dependencies that matter only at compile time. And there is runtime only for these dependencies that I don't want my code to use directly. However, they are needed when running my code. So that, for example, could be the implementation of a Java EE specification. So these configuration also happen to have relationships. And with the 4 examples we have got here, the relationship we can show is the fact that the implementation configuration extends from the API configuration. That means that anything which is declared in API effectively will go through the implementation part. So that's good. But what does that mean, that API versus implementation? Why is it so important? Well, the thing is, if you know how Java works, in order to build a module, you need a number of things. But the things you need to build and the things you need to run are not the same. And so in the context of Gradle, building means I need the API, the implementation, and the compile-only dependencies. And because implementation extends API, we could say I need implementation and compile-only. In order to run a module, what you need is the API, the implementation, and a runtime only. So we've got common bits in there, that API implementation group, and then different things, compile-only or runtime-only. So how does that get represented? Well, Gradle creates class path configurations. And so on the one hand side, you've got the compile class path, which extends implementation and compile only. And so that means that any dependency declared in API, in implementation, or in compile only ends up in that compile class path. On the other hand, we've got a runtime class path, extends implementation and runtime only. That means that dependencies declared in API, implementation, or runtime only will be part of the runtime class path. However, there is no way a compile-only dependency goes to the runtime class path, or vice versa, a runtime-only dependency goes to the compile class path. So that gives us an idea already that Gradle will use configurations in order to perform actions on the project I'm talking about. But it doesn't stop there. Then you've got the same concept of API versus implementation transitively. It's what Cedric showed, where the CLI project couldn't see the SLF4J APIs unless the Git utils project declared it as an API dependency. Of course, the alternative would have been to say, oh, my CLI project needs SLF4J, I'm declaring it immediately as a dependency. So that's also, of course, an option. And so transitively, what we're talking about is again building and running, but this time it's not building a module, but building against a module, and not running, but running against or with a module. And so when you build with a module, you need its transitive API dependencies. So if I create a library and that library exposes a Guava type via one of its return types, well, my consumers better know about Guava. Oh, my library declares Guava as an API dependency. On the other hand, the fact that my library requires an HTTP library to do some requests in the background while I'm using it, that doesn't leak through my API. So it's an implementation dependency, or a runtime-only dependency even. And so to run against that module, you need a different set of configurations. And if you remember the previous text slide, you can see that already between API implementation and these runtime and compile only, we're combining them in different ways. And that's what happens when Gradle creates these elements configuration. You've got the API elements and the runtime elements. And as we've discussed, API elements needs to extend from API. See, no compile only there. So API elements is not the same as compile class path. Runtime elements extends from implementation and runtime only. there you could wonder, that really looks similar to runtime class path. So what's the difference? Well, we'll get to that in a moment. But with that explanation, what should become clear for you is that configurations in Gradle have evolved to now represent three different and distinct concepts. One of them is a bucket for dependencies, a place where you declare your dependencies. Another one is something that can be resolved. These were my class path configuration. And the third one is something that can be consumed. These were my elements configurations. So let's go over these three aspects of a configuration a bit more in detail. The bucket is the simplest one. It's a named list of dependencies. It's something that a plugin or the standard Java plugin of Gradle offer you in order to declare your dependencies. Usually they carry definition of can be consumed, can be resolved with false. For example, Cedric hinted at the compile dependency that you should, configuration, sorry, that you should no longer use. That's because compile sadly is or should be a bucket, but has both consumed and resolved attribute to true for backwards compatible reasons. What is a resolvable configuration? It represents a consumer. It's something that has a given usage and will try to get the dependencies it points at. And of course, usually it doesn't carry its own dependencies, it gets them from the buckets it extends, which can be one or multiple as we've seen. Property-wise, it has the can be consumed false, can be resolved true, seems to make sense. A consumable configuration represents something that my library or my library produces. It carries artifacts usually attached with it. And it also extends from one or more buckets because it explains that my artifact requires these dependencies. And it has the properties can be consumed true, can be resolved false. So with all these types of dependencies, well, the question then becomes, how does Gradle match consumers with producers? You realize that in the example project Cedric did, the Git utils uses its compile class path in order to compile itself. But the Git utils project also exports an API elements and a runtime elements, and that is what the CLI project needs when it's either compiling or running. How does that selection work? How do we match the compile class path of the CLI with one of the produced variants of the Git utils project? Well, that's where Gradle comes with attributes and variant as the answer. The variant term will be familiar to the Android users out there because this is a really, really prominent concept in the Android world.
It's slightly different though. So
yeah, there are slight differences, but it still is similar in ways as well. So let's go with a bit more definition so that you understand what we're talking about. What is an attribute? It's a named thing which is typed and has a value. And it can have compatibility and disambiguation rules. And we'll exemplify those in a minute. Then you've got variant. The variant is effectively the consumable form of a module. It has artifacts and or dependencies. Both are optional. Of course, a variant that has nothing would be pretty much uninteresting. So it usually has at least one of the two, but it can have both. And the identity of a variant is effectively its attribute set and their values. So, how does that work? Well, let's say I need to compile against a project. My consumer is that CLI project, my producer is that Git utils project. And let's say for the moment that the only thing the consumer says is, I'm compiling, so I'm using the compile class path, and the producer just has the runtime elements. So what happens is that the compile class path carries attributes, and these attributes, because we are in a resolvable configuration, are requested attributes. On the producer side, we also have that variant, and that variant also has attributes which are the values of that produced thing. And here what we can see is that the compatibility rules of the usage attribute will tell us that if I ask for Java API, having Java runtime jars is okay. And we all know that's the case. I mean, it was the first slide about why dependency management. When you do compile and create a jar of your library, it can be used to compile another code that depends on it. And so all is good. We select our runtime element variant. Now, what happens if actually the project exposes an API elements in addition to the runtime elements? Well, we see that what's new is that API elements, and it has a Java API jars usage. So here, compatibility-wise, both work. The problem is Gradle can't use both. We need to pick one. We need to have only one in order to compile. And here, what we will say is, well, API elements is actually a better choice. It matches closer, so it's the disambiguation rule we talked about. So these are the it's an example of the disambiguation that happens based on the usage attribute. Now, when I need to run, well, running is slightly different. The producer has the same information. However, the consumer is no longer resolving the compile class path, it's resolving the runtime class path. And that runtime class path provides you with the Java runtime attribute, value for the usage attribute. What happens here is that this attribute is not compatible with the Java API jars. We could imagine that the Java API jar is actually a shallow jar. It just contains the classes from your public packages. And in those classes, it doesn't even have the code. It just has the method definitions. However, good news, Java runtime jars is a compatible value. And so here, at the compatibility layer, API elements gets eliminated. And so there is no disambiguation to be done. We can select our runtime elements. Now, this system worked for a long time between Java projects, but since Gradle 5.0, it works exactly the same with Maven dependencies. And so what happens is that Gradle will map, when it parses the metadata of a Maven dependency, Gradle will map the Maven scope concepts into variants. And what happens, to be short, is that the runtime scope of Maven gets mapped to a variant that has the Java runtime jars attribute. And so that's what we're going to use. The compile scope gets mapped to the compile variant and has the Java API jars. And so that's one of the things that impacted a number of people migrating from Gradle 4 to Gradle 5, is that suddenly at compilation time, dependencies were disappearing. Yes, we were removing the runtime scoped dependency of that Maven dependency, so the transitive runtime scope dependency, were removed from the compile class path. And if you happen to depend on them by accident or unknowingly, well, that was made very obvious to you because you had a compilation error and you needed to add them to the proper scope. Sometimes it was actually the fault of the library, the dependencies were wrongly declared, and an updated version of the library was published that fixed the metadata. So that gives us an understanding of how the matching works. I've used the usage attribute to exemplify those because it's the simplest one to explain, but Gradle has a number of core attributes. The usage attribute, we've just discussed it, usage of a variant, Java API, Java runtime are examples of values. There is also the category attribute, which indicates the category of a component, whether it's a library or a platform. In the Gradle world, there are different components. But when you look at the Maven world, the library is what you usually get when your Maven POM indicates a packaging jar. However, we all know that, you can use any Maven POM file as a BOM, as a bill of material, where you extract information about dependency versions. And that, for example, is why a Maven dependency can act both as a library or a platform in a Gradle build. And we'll see later exactly what that means, the platform aspect. And then the last one we have is the bundling, which indicates how dependencies are handled. And that's, for example, regular, which means we expect the dependencies to be transitive, or embedded, which probably is a good indication that there are a restricted set of transitive dependencies because the rest has been embedded inside my jar. So these are like the generic attributes that you will find also in the native world. And then, of course, we have one example here of a ecosystem-specific attribute. In the context of the JVM, we have the Gradle JVM version, and that attribute is used to indicate the minimal JVM version compatibility. So whenever you create a project in Gradle, you tell it, well, that's a Java 12 project as a library, but on the other hand, I've got a Java 8 project that uses that library. Well, Gradle will be able to tell you there's something wrong there. The bytecode level doesn't match. And so the value of that attribute is effectively the simplified Java version. So attribute usage normally is something that as a user, if you're a simple Gradle user writing build scripts, you shouldn't see much of it. However, it becomes important for plugin authors or more advanced usage if you're even trying to build an ecosystem like the Kotlin ecosystem. Attributes can be declared at the configuration level. It defines an expected value on a resolvable configuration, and it defines an exposed value on a consumable configuration. They also can be declared on dependencies. When you do a dependency declaration, you are trying to resolve the dependency. So it overrides the expected value for that dependency. It is not a way to mutate whatever the producer said for that attribute. And they also can be declared when retrieving artifact, which is something that's heavily used by Android behind the scene in order to transform, for example, a simple Java jar into a Dext AAR or things like that. From this chapter of the presentation, the main point we want you to come out with is that there is strong modeling inside Gradle about dependencies. There is really a semantic meaning with what's done, and it really helps when you understand that and play with it. And there is a semantic difference between compilation and runtime. There is a semantic difference between building a library and building against a library. And it's for us and for Gradle, it's really important to say a module must be able to produce more than one variant. And when you do that, it needs to be richer than what's available, for example, with Maven in Maven with classifiers. And I'll let Cedric drive you through the next section.
Okay, so thank you, Louis. So now we want to understand a bit more about all those versions number that we see in the wild. And we're going to talk about a concept of rich version constraints in Gradle. So what does it mean to have a version number actually in a build file? And what does it mean to have a version number in a POM file or IV file or whatever? So if I see 1.1 in this build file, does it actually mean that I need 1.1 and nothing else? Or does it mean that when I started to write that library, actually the latest version of my dependency was 1.1, so I never tried something before, but maybe it works? Do you know if it works with 1.2? Maybe. Maybe it doesn't. How do you tell this? And actually the tools we have to explain that are extremely poor. So with our job, actually, the job we do with dependency management is to make sense of all those version numbers that we see in the wild and try to understand. And most of the problems you have in dependency management come from those version numbers because they don't mean anything. So we're trying to get some meaning out of this. So what does it mean? In particular, when you see something like using latest.release, or if you see a dependency on 1.2 beta 3, does the beta is actually something important? Can I upgrade to something which is a final? Probably, but this is obvious there. But yeah, there are many different notations, like the snapshot notation in Maven. What does it tell? Is it just because I'm actually building something locally and just want to have a try to use this dependency, but when I publish, I must make sure not to publish a snapshot dependency, otherwise it's going to be a nightmare for my consumers. So there is a meaning on those version numbers, and often it's not enough. So to give this meaning, what we introduced is what we call the rich version constraints. And this is where you're going to start to use this version block there in Gradle. So what you can see is that I just modify this example that we've seen in the code, live coding. And I'm using Pico CLI again, but I'm not specifying any version number anymore in the notation, the string notation, instead of using this block. And I use two different words. I'm saying strictly 39240 excluded. So I'm saying if you use this dependency, it must be between 39 and 40. But within that range, actually there's a version I like because I tried this one and it works. And it works for me. So I'm going to say, yeah, if nobody else cares, actually use 395 and it should be fine. So I give much more to the engine because I'm telling it, if something is beyond the range, you should fail. There's no way it would work. And if you're actually finding a transitive dependency that wants, say, 396, yeah, use it, that's fine. It should work. So what we have is that we need to deal with the compatibility of all the metadata we have published with Maven, Ivy, etc. So if you don't use that version block, we have a special meaning for this version number that you have. And this is called the require block. And basically, this is really simple. When, in most cases, when you see 1.1 in a build file, it means I can probably live with anything higher than this. But lower, never tried, maybe not. So yeah, we try to upgrade. And that's what most build tools actually do. They optimistically upgrade dependencies. So this is the meaning of require. I've shown in the previous slide the strictly, which is something much stronger. It says, if it's not this version, you should fail the build. There's no way this can work. So you will have to take a decision, and actually it's part of the second webinar to help you decide how to choose in this context. So strictly is much stronger, so be careful when you use strictly because it has a strong meaning and the build engine will enforce these constraints. And the last one is just something like prefer. And in most cases, this is actually what you say. This is what you want to say. If you don't care, say prefer. Yeah, I prefer this version. But if anybody has a much stronger opinion than me, it's going to use require, and require is going to win. So we have those three keywords, require, strictly, and prefer. And actually, if you go to the documentation, we have a table that helps you understanding in which case you should use which notation. So
the one that wasn't mentioned and that you see as the fourth or the fifth column is reject.
Yeah.
And so that's really the way that you can express, well, you know, in the range of version that I accept, for example, I've tried that specific one and that one has a known issue that's tripping with my code. So please don't use that. Like don't use, if you look at the last row, 1022 excluded, but don't use 14.
Yeah. So exactly. So that's also a reason why this human readable descriptor because is super important, because there you can explain actually I rejected this version because of this reason. So it would be seen in the dependency insight report. So a good practice basically is to say you should never use a range in a prefer. It should be a require or a strictly, because what you're going to explain is if you use semantic versioning, typically is that, yeah, I require something between 1.0 and 2.0. And you know that this library is using semantic versioning, so anything starting from 2.0 is not going to work or is likely to break my build because it has binary breaking changes. So you're going to say, I'm going to require something within that range, and I prefer the version that of today that I tested, which is 1.5. There are different combinations. Sometimes what you want to say is just I don't care, use the latest release whenever it's available. And then we have a slight problem because you said builds should be reproducible. So what happens if 1.6 is released and my build file is stating latest release? Well, actually, if I come back and build again, it's going to upgrade, right? So, yeah, we have a problem there, but probably we can do something to fix that. This range, this latest.selector, latest.release, latest.integration is a special notation that we use to say this is dynamic. Actually, this is not fixed in time. A snapshot changes, ranges, the version, what versions you can find in a range change over time. And the latest release changes over time. So Gradle caches those. And you have some ways to tweak and tell, yeah, if you used a snapshot, maybe you should just cache it for 24 hours. And if you really want to kill your build performance, you can use a timeout of 0 seconds and it would check every time if actually this dependency has changed. So you have that for snapshot, it would be the cache changing modules that you would use. And for ranges, we just don't check on the repository every time if you have new versions. We just cache that for 24 hours. And if you have new releases, you need to refresh. And there's that -- refresh dependencies flag, which can be used to do that. And this is actually something that we get often. -- refresh dependencies does not mean please download the dependencies again. It means on the dynamic versions and dynamic modules or changing modules, please refresh the data because new versions came out of there. And try to resolve the latest again. So it has absolutely nothing to do with the Maven Local cache or something like that.
Though if you do refresh dependencies all the time, you will incur a non-neglectable cost on your build, because Gradle will still check for all metadata, whether it has changed or not. So it will still issue head requests, even for fixed version. So
often if you have a problem of performance, it is likely that these dynamic dependencies are in part of the problem. Dependency resolution, I mean. So I said that we had a problem with that latest.release notation. And actually we have a solution for that, which is called dependency locking. And the idea is that I'm giving this range and I'm saying, yeah, choose anything from 10 to 20, but actually within that range, today I'm pinning this version to whatever has been resolved the moment I've done that. And we generate what we call a lock file. And this lock file has to be checked in your sources. And whoever is going to check out the sources and build again is going to use that lock file. So we're going to find the exact version of the dependency within the range that, I don't know, Louis used when he was building that application. And it becomes an explicit decision to upgrade a dependency within the range. So we have options to do that. And basically, the idea is that you can lock configurations again. So it makes only sense on configurations that you can resolve. So compile class path is the example. Runtime class path is another one. Test runtime class path is. Compile is not. Unfortunately, if you do the second one, if you do dependency locking, please lock all configurations, what is going to happen is that compile is going to be resolved, but it doesn't have any meaning. So for the reasons we explained before, the compatibility, backwards compatibility reasons. So this is just a convenience. Be aware that actually what Gradle is going to do is to create a single lock file per configuration. So it's going to create a lot of files if you do that. And most likely you won't use all those files actually. So the reason we do that is again because there is a semantic associated with the runtime class path and a compile class path, and it's not because in the runtime class path you resolve to comfoo 1.2 that actually the compile class path is going to use the same version. It's just an example. Most likely in the tests versus runtime you have more differences than in compile versus runtime. All right, I hand it over again to Louis for dependency constraints.
Okay, so we've seen the way that we can do rich version declaration. But what happens when you want to tweak the version of a transitive dependencies? Normally, dependencies that you declare in your build file should really be about what your project uses for real, like for compilation or at runtime. However, sometimes the version of a transitive doesn't match what you want. And so that's where Gradle introduces the concept of dependency constraints. It effectively tells something about a module that may or may not be found in the graph. And it doesn't matter at which depth. And so what happens is that you can use a dependency constraint to provide extra version information on the transitive dependencies. And these constraints, they will not bring the artifact on your class path, compile or runtime. What they will do is they will impact another dependency declaration from the graph. And so that means without a real dependency, the constraint just is a no-op. It doesn't do anything. And so here, for example, we see a block that we could have added to the project Cedric showed earlier, where we put a constraint on the SLF4J API and we say, well, actually, I'm interested in version 1.7.26. If I put that on the CLI project, well, the CLI project still doesn't see SLF4J API for the compile class path. However, it will upgrade SLF4J, which was 1.7.2 to 1.7.26 for the runtime class path.
So you mean that if I find a bug in SLF4J, I can actually upgrade without adding an explicit dependency on my project?
Yes.
Or using an exclude?
Exactly.
Awesome.
Yep. So what we do with constraints mostly is we use them to implement the recommendation. So first of all, the constraint can carry all the rich version declaration that Cedric showed on dependencies. It can be reproduced there. And so what you will find sometimes is somewhere in your project, you define a number of constraints, and then these constraints are then used to add the dependencies. Like for example, in a multi-project, you could have an all project that creates the constraints for all the sub-projects. And in specific sub-projects, you decide which dependency you really want, but when you do that, you do it without a version. And that gives you, it's one way, for example, of centralizing the version. We will see more ways later on. So dependency constraints do participate in the graph resolution. They do not override preferences. So they are constraints in the sense of constraints in logic programming. When Gradle resolves, it looks at all the constraints, all the version constraints, whether they come from a real dependency, from a dependency constraint, and it does the resolution. That resolution aspect, the conflict resolution, is also one of the things that makes dependency management complicated. And that's why we wanted these fundamentals, and we will talk about conflict resolution and handling conflict in the second webinar.
All right, so now we're going to talk a bit about something that is often asked, which is how can I share basically some dependencies between my project? And by that, I mean dependency versions. So it is super common that actually in a single repository, in a multi-project build, you want to have the same versions of a library on all those different projects. So what can we do to actually do that? So our answer now, at least in the Java ecosystem, is the Java platform plugin. So a platform, in our terminology, is basically a set of constraints like what we just explained. So it means that we're going to have a lot of constraints and say, yeah, if you see SLF4J, you're going to use this version. If you see Hibernate, use this version. But it's not going to say you must have this dependency. It's only if you see that it's going to be used. Just platforms, as a side note, can also have different APIs and runtime dependencies. It could be that a platform is actually something like a Tomcat or whatever, and you have some dependencies which are there when you compile and not when you execute. So, yeah. Also, potentially you can have some explicit dependencies there. Not going to talk about that today. So the first step, if I want to make my project setup better, is actually to introduce a new sub-project, which is going to be my platform project. And I'm applying the Java platform plugin. And there, the only thing that I'm going to do is just to define some constraints. And that's all. This is all I have to do. So I'm just going to say, yeah, no, if you see SLF4J API, it's going to use 1726. And we're done. I define the platform. But now we need to use that platform from the other projects. And from my CLI project, what I'm going to do is just to add a dependency. And I'm going to say, yeah, now I have a dependency on this platform. So I need to use this special keyword, platform, there, which is telling Gradle, actually, I'm not trying to fetch any kind of component. I'm trying to fetch a platform component. And this is where the category attribute comes in action, if you remembered what you said earlier. So we have a component category, which is the platform one. And now, just doing that, I don't have to specify a version for SLF4J. It's going to inherit that from the platform. If you remember the build file I have defined, actually it was duplicating the version number for SLF4J. So one thing that you can do is actually to extract this version into constant. This is actually using the Kotlin DSL. You can do that exactly the same with the Groovy DSL, doesn't matter. The idea is that because SLF4J API and Simple are actually sharing the same version number, I'm going to extract that. And the good thing is that if I actually move this object depth into the build source directory, I can have completion there. So that's pretty nice too if you want to use dependency versions specifically in different submodules. We won't have time to mention that in this webinar, but actually there is something special about SLF4J there. The two versions should always be the same, right? And it would be nice if we had a way to do that. And actually Gradle provides a way to do that automatically. So even if I didn't select the same version there, there's a way for Gradle to align those components to the same version. So what happens if actually you try to publish a platform? Well, if you publish as a POM file, it's going to be equivalent to a Maven BOM. And this keyword, the platform keyword that I use as a dependency, is also something that you can use if you have a Maven BOM. So you can consume a Maven BOM as a platform, and Gradle would use that. But the opposite is also true. So if you publish this platform, it's going to be a BOM. So yeah, 100% compatible with whatever you have with Maven. So that's also something interesting if you live in a mixed world with both Maven and Gradle projects. I guess it's time to wrap up this first webinar.
Yep. So we've seen a lot of concepts. Even with those fundamentals, we couldn't go into all the details. So you'll find, and we'll share a presentation, a series of documentation links that really will help you go deeper in these concepts. You can also, of course, for Gradle Enterprise, if you're interested in viewing the product, request a demo. You've got the address there as well. So what's part two going to be about? Well, part two is really going to be about pretty much what we've said until now is really interesting and all is cool, but the real world is way more complex and there is bad metadata. Yeah, it is. And there is bad metadata out there. There are conflicts. The Android folks are used to that. When you upgrade a library, it tries to upgrade some Android core library, and suddenly you've got this joint version and Android will fail on that. I mean, there are a number of things that needs to be taken care of. And we want the second part to be mostly focusing on that, with also showing you some of the more advanced features of dependency management in Gradle. To be confirmed, but we're looking at a date of June 6th for that follow-up webinar. So we'll be happy to welcome you back if you want to know even more on the topic.
Yeah. So typically, if you ever had, say, two different bindings for SLF4J in the class path and had to exclude one over the other, there's a better way to do that with Gradle, and we're going to explain that in part two.
So I think it's now time for us to go look at the questions. While the webinar was running, I saw a couple questions that are really about the Gradle wrapper, setting up Gradle projects and all of that. We're not going to answer those here. Please have a look at the documentation, have a look at other webinars or even online trainings that are available. These are the basics about generating a Gradle project. If you have two separate Gradle projects, project A and B, which are not in a multi-module, is there a way we can add project A as a dependency in project B when project A has never been published, so it is not available in remote or local repositories? Yes, this is called composite builds, and so it's a feature that's available. We will most likely cover that in a follow-up webinar. I can't swear it's going to be the next one because we still want to focus on mostly external dependencies and the like, but that's an option. Do you have to explicitly set versions of the dependencies in the Gradle code? I think we answered that. Yes, whether it comes from a constraint or the dependency, Gradle won't select a version. You could, of course, say that you want plus, which means any version works, but that's probably not what you really mean anyway. So yes, to set versions.
So we have a question, is scope compile equal to implementation? Almost. There's a big difference if you are the producer, though, is that the implementation dependencies would leak to the consumers. So again, don't use compile, because everything you declare in compile is going to end up in the compile class path of the consumers. So it's basically the same as when you have a Maven producer that declares a dependency on compile scope. Then when you compile against this guy, you get the dependencies you don't want. So you start coding, open your IDE, and you see dependencies that you should never see.
So a question about if I use implementation, then the dependencies task won't expand my implementation configuration when I'm trying to diagnose a dep issue. Well, we've explained that. It's because implementation is a bucket. What's resolved is either compile class path or runtime class path or the test equivalence.
So there's a question we often get that we didn't really answer, which is, how do I force Gradle to re-download all the dependencies? There is no task to do that, and the real answer is, why would you ever want to do this? So as we explained, actually Gradle knows everything about dependencies. And if you have to re-download the dependencies, it can only mean one thing, that the artifact that you fetch from the repository changed. So if it is the case, and that you have a fixed version and that actually that artifact changed, you have to tell Gradle, actually this thing is a changing module. So in the dependency block, you would say, this dependency is changing. And Gradle would cache it for 24 hours, and that every 24 hours it would fetch the new version, or use -- refresh dependencies, and it's going to check again. But if you don't put that changing flag on a fixed version, and that you run -- dependencies, it's not going to download again, because a fixed version implies the artifact doesn't move in time. It's always going to be the same. So Gradle tries to be smart and not eat network when it's not necessary. So it's never ever going to do that.
Okay, another question is, what happens if a library is needed both for compile and running tests? Well, I hope you understood the extension of the graph that was shown mostly for compile and runtime. If you add the test compile and test runtime class path, they also inherit from the implementation configuration. So the extension mechanism works. So no, you do not have to redefine a dependency. If you define something in API, it will be available in all the class paths. If you define it in implementation, the same. It's only if you start defining things in compile only or test runtime only that suddenly dependencies are only available on a restricted set.
So this is a question about importing Maven bombs. So I was probably not clear enough. The notation to import Maven bombs is exactly the same as the one with native platforms in Java, with the Java platform plugin. So you just do platform, then the coordinates of the bomb. That's all.
So we've got a question about using the Gradle API. The IDE doesn't help. Again, that's a topic about the DSLs, but that's one of the motivation behind the Kotlin DSL over the Groovy DSL. So again, there are specific content available for that.
We also have a question regarding snapshots, and this is again about communicating between projects locally, etc. So what if you're in offline mode and you can't actually publish something on a repository or whatever? So we have a concept that we're probably going to mention in the second webinar, which is called the composite builds. And this is a really good use case for that. The idea is that we substitute dependencies, binary dependencies with source dependencies. So instead of having to publish your library, you don't have to. It's just going to be Gradle picking that repository or picking that external project using the sources building for you, and you don't have to publish anything.
So a question on, is there a way to debug a class path dependency? I'm going to assume class path here refers to the configuration that is used for adding dependencies to the build script class path. And the answer is yes. The task is then not dependencies, but build environment. And so if you do that, you get the equivalent output than with dependencies, but for the class path of the build script itself. So you can look at potential upgrades in transitive dependencies of plugins, like is there a Guava conflict or something like that. So yes, it's possible. The documentation is out there, but with build environment, capital E, you should be able to look at that in the documentation.
So there's also a question which is related, which is how do we list all the available configurations? So something I didn't show in the demo, but if you don't specify when you run the dependencies task, if you don't specify any -- configuration, it's actually going to list all the configurations. It's going to list all the configurations, including those which are actually deprecated. But if you read closely, it's going to tell you that those configurations are deprecated.
Corporate Artifactory requires authentication. How can credentials be provided for the repository definition? On the links slide, there is a link directly to repository section, and yes, it is supported. Of course, we don't support all the authentication mechanisms available out there, but most of them, so have a look there. Does it every time goes to the remote repository to get the dependencies, or is there anything in the local? I believe we've answered that. Gradle should not go back to the repositories. If it does, either your build is doing something funky, or you've tweaked like the changing status, or you're effectively using dynamic versions, but otherwise there is no reason for that.
So I'm just seeing one question, which is there a comparable module dependencies mechanism for C++, Python, etc.? So short answer is yes, and it's called Gradle module metadata. And we're going to show that in the next webinar more in detail. But if you use Gradle with native today, so the native plugins for Gradle, they're using the Gradle module metadata, which has exactly that.
So one question about the mix with system dependencies, like the example is the Oracle JDBC drivers that are not available on a repository. We've said it, you can define effectively a repository, which is a folder on the drive, and then the way you reference the library is by its name. And so instead of using a group name version, you will just give it a name version, and then it will recompose both of these by adding a dash in between. Again, that's in the documentation on how to declare dependencies.
Okay, so I think we'll have to wrap up now. Thanks again for attending this session. Hope you liked it. Don't hesitate to send some feedback. Second, you said should probably be on June the 6th. You're probably going to get an email with the date confirmed and with the outline of everything we're going to discuss there. Thank you.
Thank you for listening. Goodbye.